Okay. All right, let's begin lecture 6. We're continuing our discussion on statics of particles. Let me talk a little bit about the announcements, particularly about homework 2.1. There's a couple things I wanted to bring up. First off, the grades are posted. That one was a little bit of a difficult assignment to grade because there wasn't a lot to it, and so my TAs were going through all the assignments, trying to be as fair as possible. It's a little difficult, admittedly, with this assignment. The assignments moving forward are going to be much more structured, and I think it'll be a little bit more straightforward. And that'll become clear probably after today. A couple things I will mention. Number one, the homework's graded except for, I think, maybe 4 of you. If your homework is not graded yet, it's because you actually did the wrong problem. There was about 4 of you that did the wrong problem in the book. So what I'm going to do is, I know that this textbook is laid out maybe a little atypically, because I think that you'd probably think that most textbooks would have a chapter and then the problems at the end of the chapter, instead of how this textbook is laid out, where the problems are at the end of each section. So what I've decided to do is that for the first round, I'll give everybody the benefit of the doubt, and so what I'm going to do is grade the problems that you did, as they are. But from here on out, make sure that you're doing the the right problems. The other thing I will mention, and again, this will probably not be as much of a big deal moving forward with the assignments, and that'll become clear again after the work that we do today, is you want to make sure that you're showing as much work as possible, because what ends up happening is if you do the problem, and I'll just give you an extreme example, if you do the problem and all you do is just write the answer, it's sort of like the roulette table. It's either all right or all wrong. If there's work, then myself and the TAs, we have something to go off of in terms of awarding partial credit. So make sure that you're showing as much work as possible. Again, you'll see today, bless you, you'll see after today sort of the problems will start to get much more systematic and sort of easier to parse out what's going on. If you remember, I was out of town yesterday. I'm still catching up on emails. I think I caught up on all the ones of people asking questions about the assignment that was due today. I know that there was maybe 1 or 2 emails about assignments, or the students asked about 2.1, and I haven't gotten to them all yet, but I will get to them by the end of business today. I am assigning a homework today, and it's due Wednesday. It's not due Monday. I'm not going to make homework due on Labor Day. You all get the 3-day weekend that you are assigned. So, but we'll have an assignment due Wednesday. On Wednesday, bring a calculator, particularly either a scientific calculator or a graphing calculator that can solve systems of equations. I know we still have some folks who are breaking out the trusty calculator app on their iPhones and their Samsung Galaxies and whatnot, and I think for simple calcs, we're in class. I'm really not all that concerned about that, but we're going to start to get to a point where I'm sure that there are apps on those phones that can do this stuff, but it's going to, A, be much more cumbersome than just actually using a calculator, and B, you're not going to be allowed to use your cell phones and whatnot on exams. So you might as well bring the calculators and become familiar with the features that you need to use on the exams beyond just basic calcs. All right, sound good? Okay, let's talk about statics of particles. Let's get back into this topic. And what we're really trying to do today is not P plus Q. We're trying to do this one, P plus Q plus S. And I think that after the past couple of lectures, you would kind of get the sort of trigonometric approach to this, because what we would do is, if we wanted to determine this vector, because of our limitations with trig, what we would probably do is take P plus Q and then solve this triangle to figure out P plus Q, and then P plus Q, S, and then this triangle. So we would have like 2 trig problems to solve. And that would just start to add and add. We'd get more and more triangles to solve, the more vectors we needed to add. And to be clear, I want to make sure that everything that we're doing in here is couched in reality, okay? So there's going to be some application style problems that we do near the November timeframe. And one of the common challenges in an introductory statics course is the ability to solve a truss. And when we're doing method of joints analyses for trusses, we're going to have joints that have 4, 5, 6 different forces on them. Okay, so this isn't something that's outside the scope of reality. I'm not having you all add a bunch of vectors just because I'm mean and want you to do a bunch of trig. I'm trying to equip you with skills that you're going to actually use as engineers, and so this is something that we're going to need to be able to do, and we're going to develop a systematic approach to do that today. Now, to recall what we've been talking about, I think by now we all know the definition of a vector. We understand that it's an expression or an object that contains both magnitude and direction. Now, I want to focus a little bit more heavily on this second bullet, that vectors can be multiplied by a scalar to change their magnitude. So if I have a vector p and I multiply it by 3, it'll be the same vector, the same orientation, just with the magnitude being augmented by a factor of 3. It's going to be 3 times as long. Same orientation, different magnitude. That's key. When you multiply a scalar or a vector by a scalar, you change its magnitude, but not its direction. And that's the other than if you change it by a negative number. It's the same line of action, it just flips. That's incredibly important for the method that we're going to develop today. And again, addition of vectors follows that tip to tail fashion. Since we can add vectors from tip to tail, I want to start looking at adding up a bunch of vectors beyond just 2 vectors, and I want to look at a natural way of doing this. And to me, the simplest approach is to take vectors and split them up into components that we all recognize. And I think the most recognizable way of breaking apart a vector is to split it up into its x and y components. So if I have some arbitrary vector f, I can express that vector f as the sum of f sub x and f sub y. Remember, vector addition follows that tip to tail fashion, and again, the order of operations doesn't matter. So if I look at vector f, I can say, all right, I'll start here, I'll go over vector x, up vector y, and that's the same thing if I just traverse my original vector. Same the other way around. I can go up vector y, over vector x. So it follows that tip to tail parallelogram fashion of adding vectors. The other nice thing about splitting it up in this fashion is that if I can split one vector up into x and y components, I can split any vector up into x and y components. And so I can also develop a systematic way of describing vectors. And if I can do that, I can add up multiple vectors very, very easily. So what we've got here is, we've got this vector, we've split it up into x and y components. Notice the definition of the angle theta measured from the x-axis. If you remember polar coordinates, polar coordinates are defined by a radius and an angle theta measured from the x-axis, so we'll keep that convention consistent. So the idea is that what we'll do is whenever we have a system like this that has 3, 4, 5, 6, 7 vectors, jumped ahead a slide. Whenever we have a system that has 3, 4, 5, 6 vectors, what have you, we're going to take each of those vectors, split it up into x and y components. So we'll take vector p, split it up into x and y components. Take vector q, split it up into x and y components. Split vector s, split it up into x and y components. Now, why would we do that? Why do we bother? The reason why we bother is because it makes it so much easier to add up the vectors. I want to go back to an example I mentioned at the very beginning when we first started describing vectors, the example of the tug of war, or the example of the folks pushing the car through the snow. Okay, I said something at the very beginning. I said, if you've got the situation where, let's take the snow example. So there's a car, and there's 3 folks, and they're pushing a car through the snow. And so one person's pushing with 50 pounds of force, one person's pushing with 80 pounds of force, one person's pushing with 40 pounds. I said in that scenario that you can just add up the numbers to get the magnitude of the resultant, because all of those vectors are pointing in the same direction, right? Whenever the vectors are pointing in the same direction, we can just add up their magnitudes. There's no problem with that. So the reason that we split vectors up into x and y components is because if I look at these vectors and I've split them up into x and y components, I can take the x components and just add them up. Take the y components, add them up. And now I have a vector with sum of x components, sum of y components. There's the resultant. So it's a very systematic way of going about it. Now, I want to, before we get into that, I want to explore this concept of magnitude and orientation, or magnitude and direction, magnitude and orientation. I want to explore that a little more deeply, as it were, and I want to come up with a definition of something which will be very useful to us, and that's the definition of a unit vector. So remember, a vector is an object that contains two items, a magnitude and a direction, okay? What I want to do, and this is going to become very, very important later, particularly when we start looking at the third dimension, when we start looking at things in 3D, is we want to have a way or an ability to separate out the magnitude and the direction. So remember, we have some vector. It represents a 40-pound force going that way, okay? So what I can do is I can say that vector, which represents 40 pounds of force going that way, can be represented by 40 pounds multiplied by a vector that points this way that only has a magnitude of 1, okay? So the idea is that the unit vector is a vector that defines the orientation but doesn't really define the magnitude. It just has a magnitude or a length of 1. And so that's what a unit vector is. A unit vector is a vector that contains that directional information, that orientation information, but doesn't really have any magnitude. Its magnitude or its length is 1, okay? And so unit vectors are very, very important down the road. Whenever we have forces in 3 dimensions, what we'll do is, in order to define those force vectors, it will be very, very convenient to sort of handle it 2 different ways. We'll look at the magnitude on one side, and then we'll look at the direction. And in order to define the direction of that force in 3 dimensions, the easiest way of going about it will be, well, let's see if we can define a unit vector in that orientation. If we can define that, we can get the force vector. And so unit vectors are going to be very important down the road. The most universally applicable unit vectors, the essential unit vectors, are IJK, okay? So what are IJK, okay? IJK are 3 very special unit vectors that point along the cardinal coordinate systems. So let's just take the I vector. The I vector is defined as a vector with a length of 1 pointing towards the positive x direction, okay? So the idea is that if I'm looking right here, I'll look at this 2-dimensional image. Anytime I ever refer to the I vector, and this is a universal definition that we will always keep consistent throughout the remainder of the semester. Whenever I'm talking about the I vector, I am talking about a vector that points along the positive x direction and has a magnitude or a length of 1. So that's what the I vector is. The J vector, same thing, only it points along the positive y-axis, okay? Positive direction, all right? J also has a magnitude of 1, and because we're engineers and we operate in the 3rd dimension as well, I'm going to introduce the K vector as well. We're not going to use the K vector today, but what you're going to see about what we're doing in here and the use of these IJK terms is that introduction of the 3rd dimension actually, once you understand the concept of unit vectors and magnitude and direction, introduction of a 3rd dimension doesn't really introduce any more complexity. It might make the problems a little longer, but it doesn't make them any more difficult. And this is one of the benefits of this notation. These vectors always point in the positive direction. That's how they're defined. And so this is the convention that we use in here. When you take Calculus 3 here at Marshall, you will use this same convention in there as well. This is a universally applied definition in mathematics and physics. So what we can do for vector notation is follows, and this is going to be the notation that we're introducing today and that we're going to be using for quite a bit this semester, is that whenever we have some arbitrary vector, what we're going to do is we're going to split that up into x and y components. So we're going to figure out the magnitude along the x-axis and the magnitude along the y-axis, and the way that we're going to express that mathematically is we're going to say the vector is so much times I plus so much times j. Whatever the magnitude is along the x-axis times I plus whatever the magnitude is along the y-axis times j. Because this notation does afford us the opportunity of separating magnitude and direction, because it's a magnitude times a direction plus a magnitude times a direction. Because that's what really the I and j vectors are just a mathematical representation of only direction, because their magnitude is 1. So in terms of the math, it's just f times the cosine for the x-axis component and f times the sine for the y-axis component. And I'm just using basic definition of trig functions to do that. Just make sure that if you're going to blindly utilize this formula, that the angle is measured from the x-axis. Remember, if you measure an angle from the y-axis, you flip your trig functions, right? We always associate the cosine function with the x-axis and the sine function with the y-axis because those functions reference an angle measured from the x-axis. If the angle is measured from the y-axis, you flip those. So just be careful about that. Any questions? All right. I think that I'm sitting here doing a lot of talking and doing a lot of expression of formulas and equations, but if this feels daunting, you're going to see real quick how it's not. This is really simple. So what I want to do is I want to start off with this vector, and all I want to do, this is a really, really short example. We're just going to take this vector and express it in IJ notation. That's it. Then once we're comfortable with that, we're going to do a problem that's a little bit more real. So let me go to our class notebook here and let's walk through this. Again, I think you're going to find this is very, very simple. If the trig before was challenging, this is going to be much more doable. Okay. All right. So let's look at our vector here. Okay. So I have an 800 Newton vector, and that 800 Newton vector is yanking on this bolt here, and it's being measured 35 degrees from the horizontal. Now, I'm just going to make sure that we're all, following what's going on here in terms of our coordinate system here, x-axis and y-axis, etc. So what I'm going to do is I'm going to just put the blinders on and treat this very, very easily. Is this angle measured from the x-axis, yes or no? Yes. Yes. Okay. All right. So we know that F, which is the magnitude of this F vector, is 800 newtons. So because the angle is measured from the x-axis, what I'm going to do is just compute F cosine theta, which is again going to correspond to the x-axis, so 800 newtons times the cosine of 35 degrees, and then F sine theta, which is 800 newtons times the sine. Oh, I put one too many parentheses there. 35 degrees. So help me out. Let's do this one at a time. Let's start off with F cosine theta. Can somebody give me a value for that? We'll say, I don't know, like 2 decimal places. I know some of you are like, ugh, it's day before Labor Day. Do we really have to break out our calculators? Yes, you have to break out your calculators. So somebody give me this first one. 800 times the cosine of 35. Yes, sir? 655.32 newtons. Do I have a second on that? All right, here we go. All right, The sign. What do we got for that? Somebody else? Anybody? Yes, sir.
458.86.
458.86. Second on that? This should be simple stuff. Now, so could I then express this vector as follows? And somebody's in here probably going to see something, but we'll see. Is that right?
Negative.
Exactly. What needs to be negative?
The cosine of theta, f cosine theta.
This one right here, right? It needs to be negative because this is the component along the x-axis. Remember, the I vector points that way, okay? But the vector is in quadrant 2, the negative x-axis. So how would I define this vector in IJ notation? I would say negative 655.32 newtons times I plus this many newtons times J, right? And again, it separates. This is the magnitude, that's the direction, plus that's the magnitude, that's the direction. It is a simple, straightforward way of defining a vector. So this problem said, express the vector shown in IJ notation. That's the answer. There is a natural additional benefit, actually an additional 2 benefits to expressing vectors with IJ notation. The first is orientation, okay? When I look at that vector, I can just look at that equation and know kind of what that vector looks like, okay? It's in quadrant 2, negative x, positive y. It's longer in the x direction than it is in the y direction. I can conceptualize that. That's one benefit. Here's another benefit. Let's say I didn't give you 800, and all I gave you was this. What would be a very easy way of computing the magnitude of that vector? How would you compute? Yes, sir.
Do the Pythagorean theorem, square root of the 2, and then take the square root of the addition of the squares.
Exactly. If I give you a vector in IJ notation and I say, what's the magnitude? Just use the Pythagorean theorem. And so where that comes into benefit is when we're looking at resultants in the next problem. It's going to be so easy to determine the resultant of a bunch of vectors all at one point. Does anybody have any questions on this? Okay. Let's look at the next one. Now, I'm going to give you a sec on drawing this out and whatnot because this has got a lot going on here. So I'll give you a minute. But as you're writing, I'll do a little bit of talking. So we've got a point, and at this point, we have 3 vectors being applied. The vectors have all sorts of different magnitudes, and they're at all sorts of different orientations. Okay? So what we need to do is determine the resultant of these 3 vectors. Okay? And while you're drawing this, I want you to ask yourself, if I told you you had to do this using this tip-to-tail trig stuff we've been doing for the last 2 homeworks, would my course evaluations at the end of the semester start dropping? Like, God, he's a jerk making us do this. We're going to make this, that was a joke. And the fact that nobody thought it was funny, I'm getting a little worried about my course evaluations at the end of the semester. I'm really kidding. But the idea is that this tip-to-tail fashion of using the law of parallelograms and whatnot would be very cumbersome for this problem, okay? We're going to make it a lot simpler with IJ notation and a lot more systematic. I'll give everybody a little bit longer. I know there's a lot going on here. Everybody for the most part good? Okay, so in order to, systematically refer to these vectors, one of the things I guess I don't really like about this problem, I got this problem from an example in the textbook, is that there's no name for the vectors. So let's call this vector A. I don't know, we'll call this vector here B, and let's call this vector here C, so that we'll handle the vectors one at a time. Now, what we were not given on this problem were angles, okay? We were not given angles. But that doesn't really matter all that much because we've got these slope ratios, as it were. We know the bounds of the region in which they are applied. Let's take each vector one at a time, and let's see if we can express it in IJ notation. That's kind of the idea of what we're going to do here today. Is instead of this tipped tail fashion, we're going to use IJ. So let's start off with vector A. Okay? So vector A, we have this vector, and we know the magnitude of A is 29 pounds. And what we know is that A sort of fits in this box where this is 80 inches and this is 84 inches. Okay? So what I'm going to do is I'm going to use those values to determine this angle. Okay? So we'll call this angle theta. Let's call it theta A because we're going to have a lot of angles here. So let's call it something unique. We'll call it theta A. So let's dust off them trig skills a little bit. Can anybody tell me how to determine this angle theta A? Like, what's an easy way of doing that? The inverse tangent. That's exactly right. And we need to use the inverse tangent because in order to determine the angles, we're using these sides, right? We're not using this pounds because we can't really compare the pounds to the lengths, right? We're going to use 80 inches and 84 inches. So we're going to use the inverse tangent. That's exactly right. So therefore, theta A is going to be the inverse tangent of, and is it 84 over 80 or 80 over 84? There you go. 80 inches over 84 inches. And does somebody have an answer to that to, we'll say 2 decimal places? Yes?
43.60.
43.60 degrees. Do I have a second on that?
Yes.
If you are not getting 43.60 degrees, there are about 3 reasons. You either just typed it in wrong, you may be using the tangent instead of the inverse tangent, but really the big reason is your calculator might be in radian mode and not degree mode, so make sure it's in degree mode. Okay, so now that I've got that angle, what I can do is I can say, all right, let's do a cosine of this angle and a sine of this angle. So what is 29 pounds? So the magnitude of the vector. So we're basically trying to take the 29 pounds and determine the x and y components of the vector. Does that make sense? So what do we get for the x component? That's this component right here, the top part. 21. And it comes out exactly 21. I'm going to talk about that here in a second, but that's kind of a special circumstance with this problem. Do I have a second on that? I just want to make sure everybody else. Okay, what about the y component? Anybody else? Anybody got one?
42.05.
I got something different. What'd you get? Yeah.
19.99, so
20. Anybody else get 20? Okay, yeah. I got 20. You might want to check your decimals. Okay. All right. All right, so 21 pounds and 20 pounds. Just for the heck of it, I'm going to introduce sort of a shorthand engineering notation. Sometimes in order to refer to pounds, sometimes engineers will do that. Because before that was the hashtag sign, that was the pound symbol on the telephone. So you might see that in some calculations later. I'll use LB from here on out. I just wanted to show you that. So, would you agree that I could express this vector A as 21 pounds times I plus 20 pounds times J? Would that be a fair way of expressing that vector? Are the signs correct? Yes, they're both in the positive direction. Okay? So that is a systematic way of describing that vector. Okay? So I'll just sort of circle that. That's not my answer. I'll just sort of highlight that. Okay. So now what we're going to do is we're going to keep on doing that. We're going to do that for vector B. We're going to do that for vector C so that we have all of the vectors described in IJ notation. Okay. So let's look at vector B. Okay. I'm going to just redraw vector B down here because I don't want to keep scrolling because I know that'll get kind of annoying for you all in the classroom. So vector B, sorry, I didn't mean to do that. So vector B points like this. So vector B points like that, and then this dimension here, let's see, the vertical dimension is 96 inches, and the horizontal is 28, and then the magnitude is 50 pounds. Okay? So what we'll do is we'll determine theta B, just like we did before, and then we'll do B times cosine plus B times sine. Which, by the way, while you're doing this, I'll just go ahead and tell you, this problem is written in such a way that the x and y components come out as whole numbers. Like, for example, if you have a right triangle where one leg is 3 and one leg is 4, what's the length of the hypotenuse? 5. It's a 3, 4, 5 triangle, right? There are some triangles that are special, right? Like 5, 12, the hypotenuse is 13 and stuff like that. Like 8, 15, the hypotenuse is 17. These triangles are all special, which is why when you did the math, you got like 21 and 20. So for this problem, that's going to happen. That probably won't happen on homework assignments, so that's okay. All right, so theta B, we're going to do the same thing. We're going to say the inverse tangent of what? Somebody tell me, what do I take the inverse tangent of? 96 over 28, which equals what? Don't be shy. You just yell it out. Anybody got an answer? 73.74. All right, do I have a second on that? Yep. All right. So therefore, B cosine theta B and B sine theta B. So B cosine theta B, what is that? $14. Is that seconded? All right. And for B sine? Anybody? 48. Second? All right. So 14 and 48. So therefore, the vector B would be, hold on, get this. Is that correct? There you go. You're paying attention. That's what I like to hear. This is a negative 14 pounds. That's exactly right. Exactly right. And so now vector C. You know what? Here's what we're going to do for vector C. I'm going to give you all a sec, and I want to see if somebody can just tell me the IJ expression for C. We'll do it together, but I want to see if anybody can do it on their own. You got something? Yeah, what you got?
24I minus 45J.
24I minus 45J. Anybody else get that? Somebody else got that? That's good because that's right. All right, so let's go through that formally. Okay. So first off, let's draw the vector out. I'm going to scroll down a bit. So here's the vector, right? So it goes down like that, and the magnitude of that vector is 51 pounds. Actually, let's draw it like this. Oh, I didn't mean to do that. And so we've got this triangle here. We know that that's 48 and 90. And so we want to determine theta C. And so theta C is going to be inverse tangent of opposite over adjacent. And so, anybody got an answer on that one? Make sure y'all are awake. 61.93. And we know that's right. Oh, 61.93 degrees. We know that's right because we've already had the final answer seconded. So C cosine theta C ends up being, let's see, and then C sine theta C ends up being, and we already got those, we know that's 24 pounds and 45 pounds. And because the vector is along the positive x direction but negative y, we say that C equals 24 pounds times I plus negative 45 pounds times J. And if you wanted, you could write it like that, or you could write 24 minus 45. There is a reason I kind of like to write it this way with the parentheses, and that's going to become clear real quick. So let me box this just so it's systematic. Remember, if you remember, at the beginning of the lecture, I said that we're going to have a systematic way of doing this. It's starting to become clear, right? How it's pretty methodical. All right, everybody good? Do I need to, if I'm going too fast, let me know. Okay, let me scroll down a little bit. And now let's look at the resultant. Now, what is the resultant? Let's remember, we've been doing this tip-to-tail fashion, but really, what is the resultant? It's just the sum of the vectors, right? We're just adding the vectors up. We did it graphically and trigonometrically before. This allows us to do it arithmetically or algebraically. So the resultant is the sum of all the forces. That's all it is. So here's what I'm going to do. Here's the A vector, and let me go back so that I don't have to scroll up and down like crazy. The A vector was 21 pounds times I plus 20 pounds times J. The B vector was negative 14 pounds times I plus 48 pounds times J. The C vector is 24 pounds times I plus negative 45 pounds times J. And so look at how I wrote it. See how I contained all of the signs inside the parentheses? For me, it's just visually easier, because if I had stuck the negative out here, I might not be able to track it. But I'm going to add this up the way that you'd add it, I don't know, in third grade, just whoop. The resultant is all this up. So what is 21 minus 14 plus 24? 31. Plus, and what about here? 20 plus 48 minus 45 is 23. So the resultant is 31 pounds I plus 23. Oh. J. Boom. That's the answer. There's the resultant. A lot easier than all that trig stuff. But there's another added advantage to writing it this way. And it goes back to what I said before. How do you determine the magnitude of that vector? The Pythagorean theorem. Let's do that. Let's look at the magnitude and direction. So the magnitude of R is just that. So what is that? And I don't think this number comes out pretty. I think you got to round this one a bit. So we'll say like 2 decimal places. Yes? 38.60 pounds. Do I have a second on that? Yes. Now, let's also talk about this notation. Does this notation, so let's look at this. What quadrant is the resultant in? First quadrant, right? So we know that the x component is 31 and the y component is 23. If I wanted to determine the direction or the orientation of that vector, if I wanted to determine theta for that vector, what would be a really easy way of doing that? Inverse tangent, just like we've been doing this whole time. Inverse tangent of what? So, twenty-three. So what is that? We'll say 2 decimal places. We got an angle forming, we'll say 2 decimal places. Yes. Second. So the big thing to keep in mind is that R can also be defined as 38.6 degrees at an angle 36.57 degrees from the horizontal. So these are both the same thing, okay? If you want a real demonstration, and if you're willing to put a little bit of time into it, if you want a real demonstration of how powerful this is, remember homework 2.1, the one that I know you all had a hard time containing your excitement about? Do it this way. You'll do it in a fraction of the time. And you'll get the same answer that we did on homework 2.1. What's in the solution? It's a lot easier. Yes, sir?
38.6 should be fair.
Yep, you're right. We'll call that, we'll add like 0.1 to the mistake counter. Again, Marshall policy states that I'm allowed 7 mistakes per semester, but again, I'm the one counting the mistakes, so it's a corrupt system. I'm well aware of that. That was a joke. Any questions? You have a homework. All right, hold on. I know everybody's packing up. 2 things. You got a homework on Friday. When is it due? Wednesday. All right. Now, if you were paying attention, here's my last question. What are you bringing to class on Wednesday? Have a wonderful 3-day weekend. We will see you all on Wednesday.